Okay, so a little quick review of lesson 7.4 on rate laws. I wanted to go over this concept. Let's say we have a chemical equation. 2 moles of NO react with 1 mole of oxygen to make 2 moles of NO2. It says here, the coefficients in balanced equations are used when comparing rates for substances in a reaction. At a given time, the instantaneous rate of appearance of nitrogen dioxide, so NO2 here, the instantaneous rate happens to be that. It says to find the rates of disappearance of the reactants at that given time. So I wanted to make a point with this slide. The question says that NO2 has a rate of 3.2 times 10 to the negative 6. We don't multiply this by 2. It's already implied that this whole substance has this rate of appearance. Because it's a 2, this has 2 moles here, and this has 1 mole here, then this should have half the value of this. So the rate of disappearance for O2 is actually going to be 1.6 times 10 to the negative 6. It's half of that because it's a 1 to 2 ratio, meaning that this guy should have a rate of appearance that's double the rate of disappearance for this reactant. And if this is a 2 to 1 ratio here, then this guy should be double the rate, should have double the rate in comparison to oxygen. So this would be negative 3.2 times 10 to the negative 6 molarity per second. So that's how you find out the instantaneous rates. If you have it for one, you could find the others using the coefficients in a balanced equation. The next thing I want to go over is this slide right here. So for this particular slide, we learned that a rate law can describe the rate of the entire reaction. And the rate law contains a constant K. This K does have units. The units are different. It tends to vary depending on the order of the reactants. The rate law has the form of this. So rate is equal to this constant times the concentration of the first reactant to the m power times the concentration of another reactant if present to the n power. We learned that m and n are not coefficients. They are determined by experimental data, and they symbolize the order of a reaction. And the order depends on how these rates change dependent on how the concentrations change over time. So again, M and N are reaction orders. The sum of these reaction orders, the sum of M and N, is the overall reaction order. So they tend to run from 0 to 2, but there could also be fractions. We're not going to be learning about those in this class. That is beyond the scope of this class. Now, we also learned how to find the orders. So we said that if we happen to double the concentration here, if we double the concentration of a substance and the rate happens to double, meaning that it's directly proportional, then it's going to be first order. If you half the concentration and that causes the rate to also half, then it's going to cause the rate to also half. So that's a direct proportion. And so that substance, whatever that substance was doubled by, that substance will have a first order. So it's going to be a power of 1. However, let's say you triple the concentration and the rate happens to increase by 9-fold. Then that means that this tripling of rate of the concentration is going to cause the rate to increase by 3 squared. So 3 squared is 9. So the rate is going to increase by 9-fold. If you half the concentration and the rate changes by 1/4, then this half squared, which is 1/4, is gonna be the change in the rate. That's how much the rate is gonna change, by 1/4. We call this second order. Second order means that whatever you change the concentration by, the rate is gonna also change by that first change to the second power. So if I have doubled the concentration and it's second order, then that means that the rate is going to change by 4 because 2 squared is 4. So that's how you figure out the order. So here's an actual example. If you look up here, so I'm going to start a new page here. So we look at this experimental data. We are going to look at hydrogen first, okay? And we want to know the order of hydrogen. So what we do is we look for a change in hydrogen. So from experiment A to C, we could see that from A to C, the concentration doubles. But we have a problem. If you look at the other substance, chlorine, it also doubles. We don't want that. The reason we don't want that is because we need to have a controlled experiment. We want to know how hydrogen affects the rate, not how both of these affect the rate. So we can't use experiment A and C. So we're going to use experiment B and C. So if we go from B to C, we could see that the concentration of hydrogen doubles. So there's 2 times the concentration of hydrogen here. 1 to 0.2, 0.1 to 0.2. And look, it's the same. So chlorine is not going to affect the reaction rate. And then when we look at it from B and C from the rates perspective, the rate actually goes up by 4. It went up by 2 squared. So if we have a squared, the changes by 2 squared or 4 times, then we say that this guy is going to undergo a second order. Now if we look at chlorine, we find a change. We could use A and B. Because look, here it doubles, and here it's the same. Okay, so we could use A and B. So it doubles. So here we could see from A to B, you see double the chlorine, and that causes this doubling right here, causes the rate to increase by 2. It's directly proportional. So that means this guy undergoes a first order. So when you write the rate expression, rate is equal to K, you're going to write H2, which undergoes a second order. So what that means, it's to the second power. And then you're going to put chlorine gas, and it's to the first power, which is just a 1, or you don't have to put that 1 there. So this is the rate law for this reaction. The question says, what is the overall order? It's just 2 plus 1 is 3. So that's the overall order. The reaction order for each reactant, this one's going to be 2 for that guy and 1 for this guy. And it also says what is the units of the rate constant. So for that one, what you do is you look at your rate law and you basically want to know the units for this guy. So what you do is you isolate it by dividing by the other substances. And look, rate has units. I'm going to write it here. Rate has units of meters per, molarity per second. So molarity per second. It's inverse second, so it's the same as per second. And this guy, forgot the 2 there. This guy has molarity. This is molarity, but it's molarity squared because of the second order. And this chlorine is just molarity because there's no squared, there's only a power of 1. This molarity cancels with this molarity. So what you're left with is 1 over m squared. So 1 over m squared is the same as m to the negative 2 power. And this seconds is 1 over seconds, so it's also inverse. So these are the correct units for the rate constant. Okay, and that's basically a recap or a summary of what we learned in 7.4. So in lesson 7.4, we talk about rate law equations. So now we're not talking about a rate law, but equations. So if you take if you integrate, use a little bit of calculus for the rate law, you tend to get these equations. And it looks something like this. So I know there's a lot of words here, but look at just this green box right here. If we integrate a rate law, we tend to get this equation, where the natural log of a substance, so the substance can have a form of a concentration, like A, the concentration of A, at a certain time, or it could be the pressure of A. So it says here you can use pressure instead, that's totally fine, is equal to the natural log of A here, initially. So here is the concentration of A at a certain time. Here is the concentration of A at the beginning. So this little 0 is called naught, and it represents initial. So we don't write I, we write naught. So what is the initial concentration and what is the final concentration? And you subtract that from the rate constant, and you multiply that rate constant with time. The textbook uses this simplified version of this equation. So, however, the AP exam gives it to you in this form. So this is the equation that I'm going to be using. Okay, these both are the same. They're the same thing. You just set it up a little differently using algebra. So anytime a problem says that a reaction is undergoing a first order reaction, so the whole reaction is first order, meaning that there's only one reactant, then we use this equation to figure out the time that something changes, or we could find the constant, the rate constant, if we know the concentrations over time and at the beginning, and we know the time that it required for those changes to occur, we could use this equation. Okay, something that you have to know is that this follows a y equals mx plus b relationship. So this is like the y-intercept. Not y-intercept. This is the y part of a graph. Y equals, and then m is k, M, the slope, meaning it's a constant. X is time. And then the B, the y-intercept, would be this guy right here. So if you were to plot natural log of A with respect to time, it should give you a slope, a straight line that's negative. So it has to be negative slope. And if it is, then it's first order. Now I'm going to go over 3 examples on how to use this formula, and this will make more sense in a bit. So here's a problem. Like I asked in class, I asked you guys to ignore these 2 formulas because we're going to use the same setup as the College Board, which is this one right here, and not this one. So we're going to use this one. It's actually a little easier to use that one. So here's your first example. It says, if this is a first order process with K equals to that, and the initial pressure of a substance is 256 torr, find the partial pressure of that substance after 36.5 minutes. So look, I know it's a lot to digest, so if you need to pause it and read that question over and over again, do it. But this is how you do it. Okay, so what we're going to do is we're going to rewrite our first equation. So the equation is natural log of the pressure at a certain time, which is 36.5 minutes, is equal to the natural log of the initial pressure minus KT. So the question says find the partial pressure after 36.5 minutes. So that implies that we are gonna leave this, the pressure at a certain time, we're gonna try to leave this on its own, okay? So what we do is we plug in numbers. Natural log of the initial pressure, which says that the initial pressure is 256 torr, minus K, which is right there, and the time, which is 36.5 minutes. However, we run into a small problem because K has units of seconds and we're given minutes. So what we have to do is convert this into seconds. And when you guys do that conversion, you guys get either you convert it or you could expand it. So I'm going to multiply this by 1 minute has 60 seconds. So the minutes cancel and you're left with seconds. So what you're going to do is you're going to put natural log of 256 on the calculator, subtract by the product of this times that. And when you do this, I get 4.0558. But I want the pressure at 36.5 minutes on its own, so we have to get rid of this natural log. So the way you do that is you use Euler's number, e to the 4.0558, and the partial pressure after 36.5 minutes is going to be 57.7 torr. So you put torr right there. That's the answer. So that's how you use this formula. You could find the pressure after a certain time, or you could find the initial pressure after a certain time has elapsed. You could find the rate constant, or you could find the amount of time that's required for the pressure to change from this to that. So we're going to try example 2 now. I'm going to try part A. Go ahead and try this on your own first. and then look at the answer after. Okay, so now that you tried it, we're gonna read the question again. It says that it's undergoing first order kinetics, so that means I'm gonna be using this equation. And we want to find the concentration of insecticide, so I'm gonna put I for insecticide, after a year has passed, so a year after June 1st. And you set this equal to the initial concentration of insecticide minus KT. So according to the problem, it says we have a rate constant of this per year. It says that the quantity of insecticide June 1st, so it happens to be 5 times 10 to the negative 6. The problem says find insecticide on June 1st of the following year. So June 1st after 1 year. So it says that's what we want to find. We want to find this. So we put natural log of insecticide after a year, I'm just going to put year, is equal to natural log of the concentration at the beginning. So when they first measured the lake, the concentration was 5 times 10 to the negative 7 grams per centimeter cubed. Minus K, so K is 1.45 year. And time is going to be 1 year. What's nice is that these two units cancel out really nicely. So if it said after 12 months, you'd have to convert 12 months to 1 year because it has to match the rate constant. Now you just solve things. So natural log of I after a year. When you solve this in your calculator, natural log of this minus 1.45, you should get negative 15.96. However, we still have this natural log getting in the way, so we have to use Euler's number. So e to the negative 15.96, and then you get a concentration of 1.17 times 10 to the negative 7 grams per centimeter cubed. Okay, so that's the concentration after a whole year. So it went from 5 to 1.17. So the concentration of insecticide dropped. So it dropped significantly after a whole year. Okay. Part B. For part B, it's a separate problem. Go ahead and try it on your own, and then look, and then continue here. So for part B, it says that how long does it take? So how long implies time. Okay, and it says how long does it take for the insecticide concentration to drop? So it's dropping to 3 times 10 to the negative 7 power grams per centimeter cubed. This is the time, the final time, okay, because it says how long does it take for it to drop to this measurement. So the initial concentration is going to be this guy. So what we measured the lake to be on June 1st. So that's our initial. Okay, and we have our K there. So what we're going to do is we're going to write our equation. The natural log of insecticide with respect to time equals to natural log of insecticide at the very beginning minus KT. The natural log of I with respect to time, that's what we want. That's what we have. We know the concentration of insecticide after a certain change. So that's going to be 3 times 10 to the negative 7 grams per centimeter cubed is equal to natural log of the initial concentration, which is here, what we measured at the lake on June 1st, minus K, which we have 1.45, inverse years, and time, which is what we want. We want time. How long does it take? So I'm going to plug this in the calculator, get a number, plug this in the calculator, get a number, and then use algebra to solve. So when I do this, I get negative 15.02 for this part is equal to negative 14.51 for this part minus 1.45 t. When you solve for t, I got 0.352 years. So it takes less than a year for the insecticide to go from 5 times 10 to the negative 7 to 3 times 10 to the negative 7. So it's going to take less than a year for that to actually happen. So that's the neat thing about rate law equations. We could find the concentration of a substance over time, how much it decomposes or how much of it is left. Very similar to something called the half-life, which tells us how much of a substance, how long does it take for half of a substance to disappear, which we'll talk about in a bit. So go ahead and try this problem, example 3, and then we'll check our answer. Okay, so for this equation, it says it's first order, so I'm going to write my equation. Okay, it's slightly different from this one. It's just rearranged. The reason I rearranged it like this is because I wanted to show you. Okay, let me start over because I'm not sure if the mic was on. Here is an equation that I gave you here, but this is the one I introduced earlier. It's the same thing. I just moved this part to the right and this part to the left. It's addition, so you could flip them around. The reason why I flipped them is because I wanted to show you that this equation follows a y equals mx plus b relationship. So this is the y part of a graph, and m, the slope, which is a constant slopes are constant. So this is a rate constant. X is what's on the x-axis, so it's with respect to time, and the y-intercept is right here, natural log of a over time. And what I was saying is that if we graph this and it's a straight line, then it proves that the order is first order. So what we do for this particular problem is we plug in numbers to find the pressure after 1420 seconds. So that implies that we're trying to find this. But again, it's not concentration, it's pressure. So we're going to put pressure with respect to time. Natural log of the initial pressure. It says that the initial pressure is 135 torr minus K, which is 6.8 times 10 to the negative 4 inverse seconds with respect to time, which is 1420 seconds. And then from there, the seconds cancel, and you're left with torr. So partial pressure of PT is natural log of 135 minus that number right there, times 10 to the negative 4 inverse seconds, 1420 seconds. So I'm not sure why, but I rewrote everything. But basically you solve all of this, and what you get is natural log of PT is equal to 3.94. I want to get rid of the natural log, so the pressure after 1420 seconds is going to equal 51.4 torr. Right? You basically take Euler's number 3.94 and you get that. So that's the pressure. It dropped from 135 to 51.4 after 1420 seconds. So that's how you solve this particular problem. I just wanted to repeat something. If you looked at the equation that we were using, it says that we are using a first order process. So if we graph this natural log of A with respect to time, which is our x-axis, x and y. So if we were to graph that, we should get a straight line. So natural log of pressure with respect to time, it does show a straight line. However, you might not find it, at first you might not find it as this format. So it might not be as natural log of P, it might just be pressure. But what you have to do, if they ever give you a pressure and they tell you what is the order, or prove that this is a first order, then what you do is you take this individual value and this individual value and this individual value, natural log it. So natural log this, natural log that, natural log this, natural log that, natural log it all, and create a second graph. And if it's linear, that proves that it's first order. If it's not linear still and it's not a negative slope, then you know that it's probably not a first order. So it disproves the claim that it is a first order. Just something real quick, if they ever ask you for the half-life, you just use this equation right here. So the half-life is equal to 0.693 divided by the rate constant. So if you have the rate constant, you could plug it in here and you can find the half-life. So what is the half-life? The half-life is the time that is required for half the substance to disappear. Okay, so that is a half-life for a first order reaction. It doesn't matter what the concentration is, the half-life will be the same for that substance. And then lastly, we get into the second order. For second order, I don't have to really go over an example. It's the same setup that we for second order, it's the same setup that we have been doing. For first order, we learned that it is natural log of A at a certain time is equal to natural log of A initial minus KT, right? This is first order. For second order, it's the same thing, except we don't have a natural log. We don't have a natural log, so it's 1 over AT is equal to 1 over A0 minus KT. So there's no natural log and it's inverse. So for this one, if we graph this with respect to time, natural log of A with respect to time, we get a negative slope. For this one, because it's an inverse, you guys learn in math that when you inverse something, the graph is the opposite. It's no longer a negative slope, now it's going to be positive slope. And again, this follows a y equals mx plus b relationship. This is y, this is m, this is x, x is time, and then this is b right here, the y-intercept. So when we graph this versus time, we get this relationship right here if it's second order. So if they tell you the concentration at a given time, plug it in there. If they give you the initial, put it there, and then solve for whatever variable they're asking you to solve. So it's the same process, you just use algebra to find whatever's missing. The half-life is dependent on, the half-life is definitely dependent on concentration. So for first order, the half-life was equal to 0.693 over K. For the half-life for second order is different. So it's actually this equation. They do give, all of these equations are definitely given to you by the College Board. You don't have to memorize them, you just have to know how to use them. And that's it for that. In class, I went over another example. I said this was an example that was similar on the College Board. So here it says the following data were obtained for the decomposition of this substance. So here we have a reaction. We're given the time and we're given the NO2 concentration. So over time, the NO concentration goes down. How do you know if this reaction is going to be first order or second order? So we kind of have to do a little bit of thinking. just look at the question, look at the data, try to figure out on your own, based on what we learned, how do you know if this is first order or second order? Okay, go ahead and think about it, and then press play once you're ready. Alright, so I hope you guys thought about this. Something that I mentioned before is that when we're comparing the two equations, if we were to graph 1 over the concentration with respect to time, and it happens to be a straight line, then it's going to be second order. But if we graph natural log of the concentration with respect to time, and we get a straight line for that, then it's going to be first order. So the plan here should be to convert the concentration into natural log of that, and if that graph with respect to time gives us a straight line, then it's first order. Then what we could do is convert these numbers into its inverse. 1 over these numbers will give us different numbers, and we would plug them in to a graph, and if that happens to be linear, then it's going to be second order. So here in this slide, it talks about the plan, the steps that you could take. But what I did is I created this graph right here. So what I did is I created this graph, and here we have the time, here we have the concentration, but the concentration doesn't tell us much. What we do is we natural log the concentration to get different numbers here. And if we graph these numbers with respect to time here, we're going to get a graph. If it's curved, then it's not first order. If it's linear, then it's first order. And then we just stop there. And then we could, if it's not first order, then it's probably second order. So we do the inverse 1 over this number right here and put those numbers there. So go ahead and fill that in and then check your answer. So once you do that, you should get these numbers. And what I did after I got those numbers is I graphed them. So I graphed these numbers with respect to time here, and then these numbers with respect to time there. And then I noticed that the one that's 1 over the concentration happens to be linear. So anytime it's 1 over the concentration with respect to time, it's going to be second order because it happens to be linear, okay? And it's a positive slope. There might be a situation where the line is straight like this, and left and right, and that means that the reaction is 0th order. So it doesn't matter if the rate of disappearance does not change. If it doesn't change, then it's 0th order. So the disappearance of A is independent of the concentration in general. So just to give you a little recap, this hold on. So if we have a first order reaction, we have the natural log of the concentration at a certain time is equal to natural log of the concentration, initial concentration, minus kT. Second order is the same thing, it's just 1 over the concentration, so we don't have a natural log. And then initial minus kT. If we were to graph natural log of the concentration with respect to time, and we get a negative slope, then we know it's first order, the reaction is first order. See how it has natural log of concentration, right? So if that's the case, then it's first order. And then if you graph 1 over the concentration with respect to time, and that happens to give you a positive slope, then it's going to be second order. So in the previous example, we were given only the concentrations, and we converted these concentrations into natural log forms, and we inversed them as well. So we generated 2 different graphs, and only one of them was linear, and whichever one is linear, that will tell you what the order of the reaction will be because they have a y equals mx plus b relationship.